Hello guys, welcome back to my channel. In this video, I'm going to show you the full solution of 2020 Physics Higher Level Paper 2 in Time Zone 0. No bullshit, let's go. Question 1. There are lots of information in this question, so feel free to pause the video and read it first. When you have finished reading, resume the video. There are lots of numbers being given in this question. For instance, the mass of the aircraft is 0.95 kilogram. So I suggest right next to the diagram, you put down capital M for the big mass of the aircraft is 0.95 kilogram. And the string and package altogether its mass is small m equals to 0.45 kg. Then there are certain mass of air being pushed downward by the blades in 1 second, and the amount is 1.7 kg because it is a mass being pushed per second. So I suggest you consider this one as mass over time being 1.7 kilogram per second. Next, this aircraft is hovering motionless, which means by Newton's first law, its net force is 0. And this is the answer of part A1. A1 asks for the resultant force on the aircraft when it is hovering, so the answer is 0. Part 2. With reference to the Newton's third law of motion, we're going to give an explanation why there's an upward lifting force acting on the aircraft. Because there is a force exerting downward on the air by the blades. By action and reaction pair, the equal and opposite directional force will be exerting on the opposite body. Therefore, there is a force acting by the air on the blades. Acting on the blades, which is equivalently acting on the aircraft, upwards. For now, let's summarize what we have concluded in part A1 and A2. In A1, we studied the Newton's first law. The upward force and the downward force acting on the aircraft, they are equal, so as to maintain motionless. Next, in part 2, we have compared the upward force and the downward force acting on aircraft and acting on the air. They are equal. Then what do we do with this information? You can see that the connection is these two forces, they are both the same in magnitude. And how do we calculate the magnitude of these two forces? Let's focus on the weight first. The weight is the total mass times g. Big M plus small m times g is the total weight. This is the total downward force acting on the aircraft. And the downward force acting on the air is based on the rate of change of momentum of the air. The force acting on the air, according to the equation above, it should be the same as the weight, therefore big M plus small m times g. The rate of change of momentum is the change in mass per second times the speed of air particles. And we have all the numbers being given in the question already. They are 0.95 plus 0.45 times 9.81 equals to 1.7 times unknown speed of air particles. So just rearrange them and you will get the answer of V sub A being 8.0788. But we have to give our answer in appropriate number of sig fig, and we pick the appropriate number of sig fig depending on the number that you have used. The number that you have used are over here. The least significant figure you have chosen is 2 sig fig. So we run our final answer as 2 sig fig, 8.1 meter per second. Part 4, you're going to calculate the power transfer to the air particles by the aircraft. Power is defined as rate of energy transfer. And what was the energy transfer to the air particles? Purely KE. And the old KE of the air particles is 0 joules as they were stationary. After passing through the blades, it will be moving very fast. The new Ke of the air particles should be half mv squared. Lastly, we get the power by studying the work done over time. Therefore, it's the half mv squared minus 0 over the time taken. Then we rearrange to make m over t group up inside a bracket to emphasize it is the rate of change of mass times the speed square. Therefore, it is half times 1.7 times 8.1 square. It gives you 56 joules. Part B, let's make some drawing to visualize all the information. It was connecting an aircraft to the package, so we have big M and small m all together. The total weight is big M plus small m times g. At the same time, there is an upward force acting on the aircraft. And these two forces, they are balanced so as to maintain motionless. What was the downward force? Its magnitude is 13.734 Newton, so as the upward force, 13.734 Newton. And in part B, suddenly the wire is snapped. Therefore, it's only the big M being considered. The upward force is same as the old time, 13.734 Newton. But right now, the downward force is only the big M times g. Therefore, the magnitude of the downward force is 9.3195 Newton instead. And we'll focus on the new diagram. After the string is snapped, then we have a net force equals to ma, with the net force is 13.734 minus 9.3195 equals to the mass, the big M mass, 0.95 times a. The acceleration, therefore, is 4.6 meter per second square. Question 2, circular motion. Here we have a person in a ride known as motor. The motor is a spinning ride. As it speeds up, the floor is starting to drop out, and the passenger will have his own feet off the ground. What are the forces acting on the person? Firstly, there must be a downward weight starting from the center of mass. You may label this one as weight. Also, you can label it as W or mg. Apart from this one, there must be a force provided from the wall to the back, pointing to the left. This is a force known as the normal reaction. And you can label this one as N. However, only in this question, you should not label this one as R. Why not? Because capital R is denoted as radius. So capital R is not accepted for denoting normal reaction. Lastly, there is a friction going between the wall and your back. This friction is pointing upward so as to prevent the passenger from falling. You may label this as friction or F subscript small f. The upward force and the downward force, they are balanced, leaving the force pointing to the left, therefore the normal reaction being the net force. Therefore, in part B, we can start with the net force is the centripetal force, therefore it is mr omega square. And the net force in this case is the normal reaction. So the normal reaction is mr omega square. Apart from the horizontal analysis, we may take a look at the vertical analysis. The frictional force should be the same as the downward weight. Therefore, the mu times n is equal to the downward weight. And by putting these two equations together, we can derive mu times mr omega square equals to mg. Lastly, just rearrange and you will get the required expression, square root g over mu r. Part C is pretty straightforward. As all the numbers they are given, you can just start with the given equation. Then you substitute all the numbers in. You get 9.81 divided by 0.40 times 3.5 meter square root. Then you will get the minimum required angular speed is 2.647 radian per second. The current spinning angular speed is 28 revolution per minute, and it is equivalent as 28 times 2 pi divided by 60 radian per second. It is 2.93 radian per second. To conclude, you may compare the actual spinning angular speed is greater than the required minimum safe angular speed. Therefore, the passenger will not slide down. Make sure you put a comparison like this one. Question 3, thermophysics. We have a vegetable oil starting from its liquid phase and being put inside a freezer. So its temperature is reducing from time to time, and the thermal energy transfer is going at a constant rate. The mass of the sample is 0.32 kg. The specific latent heat of fusion is L subscript F. Lastly, the rate of thermal energy transfer is the power here, A1. We're going to calculate the energy transfer within the first 30 minutes only. Power is equal to the energy transfer over time. Therefore, the energy transfer is the product of power times time. It's 15 watt times the time, 30 minutes in second. So 30 times 60, 27,000 joules. Part 2, we are going to calculate the specific heat capacity of the oil when it was in liquid phase. What was the liquid phase? It was when time equals to 0 up to 30, because only within this window the temperature was reducing. The temperature reduced by 40 Kelvin. And the time it took was 30 minutes. Let's begin with the equation Q equals to mc delta T. The energy flow is 27,000 joules as calculated above. The mass is 0.32. C is unknown. Change in temperature is 40 Kelvin. So the specific heat capacity is 2,100 joules per kg per Kelvin. Part B. During the freezing process, you can see that the temperature remains unchanged. And what is the explanation for this one? Let's take a look at the molecular structure. When it was in liquid state, the particles, they are not bound to any strong bond between them. However, when it is turned into solid, therefore after freezing, it becomes in a very rigid and irregular structure. And this connection going between them, it's known as a bond. Forming this bond requires an energy release to the surrounding. So the description for this one is, firstly, the intermolecular bonds are being formed during this freezing process. Secondly, bonds formation is a process of energy release. And in this process, it's the potential energy among the particles being reduced is PE being reduced. Lastly, the average random kinetic energy of the molecules remains unchanged. And because temperature is a measure of the average random kinetic energy of the molecules, therefore the temperature remains constant as well. Part C, we are going to calculate the mass of liquid oil. From 0 to 30th minutes, here we have 27,000 joules of energy transfer. And because it is transferring at a constant rate, so from 30th up to 60th minutes is also 27,000 joules of energy transfer. With these amounts of energy transfer, what is the amount of oil being transferred into solid is about Q equals ml. Q is the thermal energy transfer, and then the mass is unknown with the L being 130,000. Then you can get the mass which is transferred into solid, 0.21 kg. And when you compare with the original mass, you can get the remained unfrozen mass, which is the old mass 0.32 minus the frozen mass 0.21. So the answer is 0.11 kg. Question 4. We have two loudspeakers emitting sound wave towards point P, and because these two paths they are not in the same length, so there is a certain path difference, and depending on that path difference, it could be constructively interfering or it could be destructively interfering. All you need to do is to make calculation, get the exact path difference, and relate that path difference with the multiple of wavelength. Let's begin with a title, path difference. It is the longer path BP minus the shorter path AP. Numerically is 24.3 minus 22.5, so it gives you 1.8 meter. 1.8 meter is equal to certain times of wavelength. The wavelength is deduced using V equals to F lambda. The wave speed is 340. Frequency is 850 times unknown wavelength. Then the wavelength is 0.4 meter. 1.8 meter is actually 4.5 times of a wavelength. And because it is half integral multiple, so they are interfering destructively. In part B, there is a microphone moving from position P to position Q as shown in the solid arrow here. At position P, according to our previous calculation, it must be 4.5 lambda in terms of its path difference. And at position Q, it is at the midpoint between A and B, which means it is 0 lambda. The transition from 4.5 lambda to 0 lambda is including 4.0 lambda, 3.5 lambda, 3.0 lambda until it reaches 0 lambda. To conclude, when it is 4.5 lambda, it is a destructive interference, followed by 4.0 lambda, a constructive interference. 3.5 destructive, 3.0 constructive, until you get the rest like this one. And let's count the number of constructive interference from P to Q. There is 1 constructive, 2 constructive, 3, 4, and 5 if you're including the endpoint Q. And we will describe such variation as there is a continuous variation from P to Q going between maximum and minimum intensity, and it must be a maximum intensity at Q. Apart from Q, there will be 4 extra additional maxima excluding Q. In part C, we are going to shut down one of the loudspeaker. And because previously there was a constructive interference, so their amplitude add up. It's their amplitude adding up, not their intensity adding up. After shutting down one of the loudspeaker, which means the amplitude should be half of the original. Amplitude being half, which implies the intensity should be 1/4, because intensity is proportional to the square of amplitude. Then we can put our answer like these two statements. The amplitude of the sound at Q will be halved. and the intensity is proportional to the square of the amplitude. Therefore, the required ratio I sub A to I sub 0 will be 1 to 4. In part D, we are going to study a Doppler effect. We have the loudspeaker remain stationary, but the microphone is moving away from the source. And because it is an observer being moving, then we can take a look at the wave front. The wave fronts are going as follows. They are created by a stationary source, which means no matter the left-hand side wavelength or the right-hand side wavelength, they are always the same. Then let's have this equation in our mind, starting with the wavelength being unchanged. But the relative speed of the wave is now slower as the microphone is moving away as well. Therefore, the observed frequency or the apparent frequency should therefore be reduced. And our explanation should go in the following way, not in algebra. The speed of the sound in relative to the microphone is less, therefore the wavelength remains unchanged and the frequency should be reduced. Next, part 2, we are going to make a calculation and you should choose the correct equation carefully because there are two similar equations in your formula sheet. The correct one is this one. The subscript O stands for observer, V is the speed of the wave, F prime is the apparent frequency. Here we have the apparent frequency being 845, the original emitted frequency is 850, the speed of the wave is 340, but the speed of the microphone, V, is the unknown. So you can rearrange the equation and get the final answer as 2.00 meter per second. This is the speed of your microphone. Question 5, you are given with a current against potential difference graph. And this graph is a nonlinear graph, which makes it a non-ohmic conductor. Cause all ohmic conductor must be a straight line going through origin on an IV graph. Part B, the ammeter is reading as a 20 milliamps, which means all devices right now they are connected in series. Then every single components that you can see they are carrying 20 milliamps, including the component X. Let's check the graph on the left to get the voltage of component X. When the current is 20 milliamps, the voltage is roughly 2.3 volts. So back to the diagram on the right, we write 2.3 volts here. And since everything here on the right hand side they're connected in series, so their potential difference should add up. The potential difference of the cell is equal to the potential difference of R plus the potential difference of X. So it is 4.0 equals to unknown plus 2.3. Variable resistor, and right now its voltage is 1.7 volts. Next, we take the definition of resistance, potential difference across the components divided by the current through the components. Then we have 1.7 divided by 20 milli. And the resistance is 85 ohm. Question part 2. The total power dissipated in the whole circuit. Because of conservation of energy, it should be the same as total power delivered. Total power delivered by the power supply is P equals to IV. Its current times its potential difference. Current is 20 milli. Voltage is 4. And the answer is 80 milliwatts. Or you can do 0.080 watts. Part C, we have a potential divider. This slider may point at Q, may point at P. When the slider is at Q, then the PD of X is 0 volts because at that moment, the X will be just going across the ideal wire. And when it is at P, the PD of X will be going across your power supply and going across the entire PQ as well. Then the voltage of it will be 4.0 volt. In other words, you are studying the range of currents when X is 0 volt up to X is 4 volts. And you can check its range of current going back to the previous page. When the voltage is 0 volt, the current is 0 milliampere. When the voltage is 4 volts, the current is 60 milliampere. So the range of current is 0 milliampere up to 60 milliampere. Part 2, we are going to make the position of slider S such that the current running through X is 20 milliampere. At the same moment, there is a certain current passing through PQ, which is an unknown value. And what is the total current passing through your cell? The total current passing through your cell will be this one. I of the cell is equal to the I of PQ plus the I of X, which is a certain value PQ plus 20 milliamps. The current running through the cell is greater than 20 milliamps. How about the power of the cell? The power of the cell would be I of the cell times voltage of the cell. And it is a value greater than 20 milliamps times 4.0 volts. To conclude, it must be greater than 0.080 watts. That's why it's greater than part B. However, in this question, you are not supposed to make any calculation. So you may give your answer as follows. The current running through the cell is greater than 20, since there are some currents running through SQ as well. Therefore, the total power running through the cell is greater than part B. Question 6A1. It's a definition question, so there's no much explanation. It's just a definition, you memorize it and you get the mark. It's the energy required to completely separate the nucleons, or the energy released when a nucleus is formed from its separated nucleons. 6A2. Usually when we are studying atomic physics or nuclear physics, the unit of mass is no longer kilogram nor grams because the value would be extremely small. Usually it's 10 to the power of negative 30 or even smaller. That is something not convenient. It's still correct, it's accurate, but it is not convenient. So we'll need some other units, which is making the value looks better. It just looks better. Therefore, the answer is the values in SI units would be way too small. Part 3, we are going to make a calculation to show that the energy released in this reaction is about 180 mega electron volts. It is a show that about question. Make sure your final answer is giving one more significant figure than the target's value. Let's begin with the total binding energy on the left-hand side. Binding energy on the left-hand side is the binding energy per nucleon of uranium-235 nucleus, 7.59 times the number of nucleon there, 235. And don't forget the binding energy per nucleon of a neutron. But if you refer to the definition here, you can tell there is no such binding energy to a neutron because you cannot separate a neutron into smaller nucleon. It is a single nucleon itself. If you insist, you can do 0 MeV times 1 nucleon. This is the binding energy on the left-hand side. Similarly, we can do the binding energy on the right-hand side and make sure you refer to the number of nucleon as well. Starting with 8.29 and there are 140 nucleons. It's 8.59 and there are 94 nucleons. And once again, if you insist, you can do 0 MeV, the binding energy of neutron, and there are 2 neutrons. Lastly, you compare these two and take a subtraction. then the answer should be 184 MeV. Part B1, we are going to calculate the specific energy of uranium-235 nucleus. Specific energy is the energy is stored divided by the mass, and what is the energy it gives is 180 mega electron volts, and you can convert it in joules by multiplying to 10 to the power of 6 to get rid of mega, and multiply the elementary charge to get rid of the E. Then this is the value in joules, followed by turning its mass into kilogram, because the given mass is in U, then you have to turn it into kilogram. It's 235 U times 1.66 times 10 to the power of negative 27, and it will be in kg. Put these into your calculator, then you will get 7.4 times 10 to the power of 13 joules per kg. Question B2 is about efficiency. Efficiency is the ratio of the useful power output to the total power input. So here is 36% equals to the 1.2 times 10 to the power of 9 being the useful out, and you can get the power in. So the power in is 3.3 times 10 to the power of 9 watts. Then what is the amount of fuel required to burn in order to give this power in 1 day? Let's convert 1 day into second. We have 24 hours, 60 minutes, and 60 seconds to give the target power, 3.3 times 10 to the power of 9. So the work done or the energy required is 2.88 times 10 to the power of 14 joules. And using your answer in part B1, you can convert these amounts of energy into mass of the uranium-235 nuclei. So the mass required is after the division, 2.88 times 10 to the power of 14 divided by the answer in part B1. It's 7.4 times 10 to the power of 13. So it is 3.89 kg. In part 3, we are going to compare fossil fuel and uranium-235 nuclei as a new fuel and see if there is any advantage of using uranium-235 nuclei. Clearly, the difference is their specific energy. The specific energy of uranium-235 nuclei is much, much higher. So the answer to this one is, one can obtain more energy from the same mass of fuel. Part C1, we are going to balance the equation on both sides. On the right hand side, it looks like you have no information. Actually, you do know that it is anti-neutrino, so it's 0, 0. It is a beta minus decay, so it is an electron, is 0 and negative 1. The rest is completing the math. Let's focus on the upper row. We have 94 on the left, we have unknown plus 0 plus 0. So this one must be 94. The one below is 39, such that it's balancing the left hand side 38 and the right hand side 39 minus 1. The proton number of nuclide X is 39. Part C2, looking at the half-life of your sample. Half-life is the time needed from 100% to 50% of the amount of undecayed particle. So it's from 1.0 down to 0.5. The corresponding time is half-life. It is 75 seconds. Part 3 calculates the remaining mass after 10 minutes. 10 minutes, which means it is 600 seconds. So what is the amount of mass remaining after 600 seconds? 600 seconds is equivalent to 8 of your half-lives. After 8 half-lives, how much of the proportion is remaining? If it begins with 1.0 kg, after each half-life is going to reduce by half, and there are 8 half-lives. Therefore, the remaining mass is 3.9 times 10 to the power of negative 3 kg. Question 7. there is a cylinder floating on the water surface. And according to the equation, rho, the density, A, the cross-sectional area, and G, the gravitational field strength, they are all constants, which means we can write down the resultant vertical force is proportional to the negative displacement. And if you write it in a full sentence, it's even better. It is the restoring force is proportional to the displacement in the opposite direction. In part B, we are going to make a very long calculation. Let's begin with the condition for SHM. F is equals to ma. Meanwhile, the acceleration A is the negative omega square x. So we have the first equation prepared, negative m omega square x. On the other hand, we have the given equation, F equals to negative rho a g x. By comparing these two equations, you can immediately conclude m omega square is equal to rho a g. Right now, our target is the angular frequency, which means omega is our unknown. Let's make omega be the subject. It will be rho a g over m square root. Rho is given as 1.03 times 10 to the power of 3. A is also given. It is 2.29 times 10 to the power of negative 1. G is 9.81. And then M is 118. Finally, square roots. Then you will get omega as 4.43 radian per second. Part C1, we are going to get the maximum kinetic energy of the cylinder. In an SHM, the maximum Ke is also the total energy. According to your formula sheet, it is half m omega square amplitude square. All the numbers that you need, they are given already. Let's say the mass is given as 118, omega is 4.4, and then square. The amplitude is given here, 0.250 square. Just put them into your calculator and you will get the answer, 71.39 joules. And after rounding, 71.4 joules. Lastly, we are going to make a graph sketching, and it is the variation of the kinetic energy of the cylinder varying with time within one time period. As the cylinder was originally being pushed down, so it was starting at the bottom. So the marker is going up and then falling down. This is one cycle. When it is at the very bottom or when it is at the very top, it is staying at rest momentarily because it's changing its direction. However, right in the middle at the equilibrium point, it is moving at the highest speed, the fastest speed you can get, which means it will be rest, fast, rest, fast, rest. In terms of energy, it will be 0, fast, 0, fast, 0, with the endpoint being one time period as well. Lastly, we are going to join these dots using a very smooth curve. Note that the curve that you draw should have no sharp change, no sharp turn. So the following is a wrong answer. This one is wrong. These are not accepted because they are sharp change. You need a very smooth and gradual change. Question 8 is about the electric potential around a positive conductor Q. Let's take a look at the definition of electric potential. It's about bringing a positive charge from infinity to certain points. Because the big Q is positively charged, so when you bring a positive small test charge from infinity to point A or point B, it requires certain energy. It requires even more energy when you are moving it to position A because A is very close. For instance, it may require 11 joules, but moving to position B, it just requires maybe 9 joules. So as you move from A to B, these motions is actually reducing 2 joules for the work done. To conclude, in part A, why the electric potential is decreasing from A to B, it's because the work done per unit charge in bringing a positive charge from infinity to point B is actually less than the requirement for point A. Part B, we're going to draw a graph of the electric potential against the distance r. When it is outside the conductor, its behavior is just like the natural exponential graph that you have been studying, like this one. But it's not happening the same way inside the conductor. It's something else. What's happening inside the conductor is that, firstly, it is a conducting sphere. So inside the conductor, there is no electric field. Everywhere its electric potential is the same. And it's also the same as the surface. For instance, at the surface, maybe it is 15 volts. At the center, it is 15 volts. Everywhere it is 15 volts. It's always the same potential as the surface. Therefore, the graph is a flat line when it is inside the conductor, and it will be an exponential curve outside the object. Question part C, there are too many words. Let's make a drawing to make everything visualized. Starting with the positive Q at the center, and then you have position A, which is at a distance of 5.0 times 10 to the power of negative 2 meter away. The other one is position B, and it is 1.0 times 10 to the power of negative 1 meter. Lastly, the motion of a proton moving from A to B is requiring a certain work done, 1.7 times 10 to the power of negative 16 joules. Then what is the electric potential difference here? It is V equals to work done over the charge. The work done is 1.7 times 10 to the power of negative 16 divided by the charge of the moving particle. It's a proton, so it is 1.60 times 10 to the power of negative 19. The answer is 1062.5. After rounding, it is 1100 volt. The electric potential difference is also defined as V sub A minus V sub B. So you can make a substitution like KQ over R sub A minus KQ over R sub B. And this is 1100 volts. You can rearrange to make KQ out of the bracket of 1 over R sub A minus 1 over R sub B equals to 1100 volts. K is given in your formula sheet. R sub A and R sub B, they're given in the question above, so you can rearrange to make Q be the subject, and it should be 1.2 times 10 to the power of negative 8 coulomb. The idea of potential is not limited to electric field. It's also happening in gravitational fields. And why do we need to use common terminologies in multiple fields? It's because doing so will help highlighting the similarities between different fields. In question 9, we have a coil rotating around an axis of rotation, and this spinning coil is spinning within a uniform magnetic field. In part A, you are going to give your answer with reference to Faraday's law of induction, how a EMF is being induced in this coil. Firstly, there's a magnetic flux linkage going inside the coil, and this magnetic flux linkage is varying as the coil is spinning. And because of the Faraday's law of induction, there is a magnitude of induced EMF increasing with the rate of change of magnetic flux linkage. As you spin more rapidly, there is a greater induced EMF created along the wire. In part B, we can get two equations prepared. Firstly, it is the average power being half times peak current and peak voltage. We can get the average power from the question. And we can get the peak voltage from the graph. But we don't know the peak current. Let's get the peak current first. It is 2 times the average power over the peak voltage. So it is 2 times 8.5 times 10 to the power of 5 divided by 25,000. It is 68 ampere. And getting root mean square current from the peak current is make a division by root 2. So it is 68 divided by root 2. It gives you 48 ampere. Part B2, you are going to make a step-up transformer, and the target is to, by stepping up the voltage, you should reduce the power loss by a certain factor, 250 times. If you step up the voltage, which means you are stepping down the current, the equation for power dissipation in a transmission is power equals to I square R. And R, resistance of the long wire, is a constant. So you can do power is proportional to I square. In order to reduce the power, you should reduce the current square by 250 times. So the current is reduced by square root of 250. It is roughly 16 times. Part 3, the frequency of the generator is double, and this is the only change. What is the consequence of the variation on the graph over on the left? And let's take a look at the Faraday's law. The induced EMF magnitude is the rate of change of its flux linkage. As the frequency is double, which means the rate here is double as well, the induced EMF should be double. Then the peak induced EMF will be 50 now. This is the new peak induced EMF. The time period was 20 milliseconds. The new time period should be 10 milliseconds. Therefore, your graph should complete its first cycle right over here. And its peak is happening over here. The graph is going in this pattern. This is the first cycle. And the coming cycle is here. By doubling the frequency, you can see the induced EMF magnitude is double as well, but the time period is half. Question 10, you're given with an equation. And using all the given number, you should get part A very easily. Let's begin with making the correct substitution. Planck constant is given in your formula sheets. And then the c is the speed of light in vacuum. It's 3.00 times 10 to the power of 8. And E should be in joules, which means you're going to convert 4.2 times 10 to the power of 8 into joules. Such conversion is very simple. Just multiply this given number with 1.60 times 10 to the power of negative 19, the elementary charge. Your answer should be 2.96 times 10 to the power of negative 15 meter. Part B1. This electron beam is passing through a sample of carbon-12 nuclei, and then it's found that the electron is no longer passing in a straight line. It is diffracted after passing through this sample. And what is the experimental evidence showing there is a diffraction? How does it show there is a matter waves carried by the electrons? Because of the graph, you can see at some point it looks like a maximum. At some point, it looks like a minimum. So this is a very clear evidence. And you can put your answer as, the shape of the given graph suggests that electrons may go diffraction with the carbon nuclei, and only waves can diffract, nothing else. Diffraction is the extremely clear evidence of waves is present. Part 2, we make a calculation to predict the angle theta sub 0, which is the first minimum. So we begin with sine theta 0 equals to lambda over d. It is the de Broglie wavelength of the electron. It's given at 3 times 10 to the power of negative 15 divided by the diameter. It is 4.94 times 10 to the power of negative 15. So this ratio is 0.60729 and angle 0 should be 37 degrees. Part 3, the electrons, they are now reducing their energy. They had 10 to the power of 8 eV, but now they're reducing to 10 to the power of 7 eV. So it's definitely reducing its energy. By reducing its energy, what is the effect to the Broglie wavelength? The Broglie wavelength is hc over E. Therefore, we can claim that the Broglie wavelength is inversely proportional to E, and because the E is reduced, the wavelength is getting longer. When the wavelength is getting longer, it's not that helpful in creating a diffraction over the carbon-12 nuclei, because the de Broglie wavelength is now much longer than the size of the nucleus. Therefore, there is no diffraction pattern to be observed. Part C is a very common derivation required in the exam, is showing the density of a nucleus being remained constant throughout all nuclei. Let's begin with the density equals to mass over volume. Mass of a nucleus is the mass number times the atomic mass units, U. And the volume of it is considering as if a sphere, that it is 4 over 3 pi r cubed. Next, we have A times U remains unchanged, and we are going to replace R as something else. The Fermi radius times A to the power of 1/3, bracket 3 times. This equation is provided in your formula sheet, topic 12. And next, we have AU at the top still, and then 4 over 3 pi r sub 0 cubed, and A to the power of 1. You can see that A is crossed out, leaving your answer as 3U over 4 pi r sub 0 cubed. And now this whole expression is a constant. That's why we can say the density of all nucleus is roughly the same value. This is the end of the complete solution. Feel free to leave a comment below, and I will see you guys next time.